Let's start because it's already 1:11. Okay. So anyway, so we were talking about the sequential, if you guys remember, sequential circuit, right?
Yes, latches.
We said, first we're gonna start with latches, then we will move to flip-flops, and the flip-flops we're gonna have multiple flip-flops, which is basically the SR flip-flop, JK flip-flop, D flip-flop, and T flip-flop. Those family will be actually represented by 3 tables, which is the truth table, characteristic or state table, and then gonna be the other one, excitation table. So far so good. We talked about the latches, and after we finish the flip-flops, by the way, we're gonna learn about replicating flip-flops many times, so we're gonna have what registers. Having registers, we're gonna have memory. Then combining combinational with sequential, you can build as an example processor. And while we are moving here in the registers, we're going to learn about something that's called FSM, which stands for finite state machine. Sounds good?
Yep.
Okay, so let's go to the latches. So we said, I'm gonna repeat again. Which what? Somebody said which something. What? Which chapter is this? It's not chapter. I'm talking about the whole book, right? So, what is latches and sequential circuit is the chapter after, right? So do you remember the book? Where's the book? Here is my book. So we finished chapter 4, right? So we finished the combinational circuit. Chapter 5 is a sequential machine. Chapter 5 sequential. Chapter 6 will be sequential. What was chapter 6 going to be? Chapter 6 will be registers. So chapter 5 is the sequential circuit flip-flops and finite state machine. Chapter 6 will be the shift registers and counters. And chapter 7 is going to be the memory, as I said. And chapter 8 is starting with the languages, RTL, register transfer languages, levels. Okay, so we are on chapter 5 now. Okay, now, for the latches, right? So latch, it's just a pure combinational circuit. Do you guys agree? Combinational circuit. Why we are using latch from your point of view? Storing data. Sounds good? What is the advantage of the latch? Storing data. What is the disadvantage of the latch? There is no time. How much time I can store the data, how much time I can release the data, right? Also, from our discussion last time, we found out there is one state is not used. That makes sense? So one of 4 states are forbidden to be used. Sounds good?
Yep.
Okay, now let's go into the latch. So we have SR latch, SR latch. This SR latch, implementation wise, is using two different type of technology, which is a NAND gates, NOR gate. As I told you, everything NAND or NOR, right? It's gonna be NAND gate or NOR gate. As a students, even and as a somebody's learning digital logic, what exactly you need? What was in his notes? 1-4 states are what? What 1-4 state what?
I think it says it right there, Professor. It says one of 4 states.
Oh, 1 of 4 states, yes. 1 of 4 states. There are 4 states, right? Are forbidden to be used. Alhamdulillah, this is recorded video. You can watch it again. Okay.
0, that was the undefined state.
It depends, because we're gonna try some technology. It will be something else.
I see.
Okay. So
That's the
anyway,
arbitrary numbers, man.
yeah, it's basically depends on if you are NOR or NAND. One of them 0, 0, the other one is 1, 1. You know what I mean? Okay. Anyway, so if I'm studying, what exactly I'm expecting? Basically to study and see whether this latch is really storing data or not. All right. So this is basically my expectation. So the latch, it's a box like this. It has 2 inputs and it has 2 outputs. The latch is basically based on set, reset. S is set, R is reset. Set, reset. And that's called latch. And the output is basically Q and Q complement. So Q complement are the outputs and the input are the set and reset. That makes sense?
Yes.
Okay. Now, what is inside? It's a kind of what, if I'm storing, so that means there is a kind of feedback. So we are looking for feedback control. How? If I am NAND, I'm gonna be like, here is one NAND and my S, and here is another NAND and my R, and then here is R, the redness, and here is the R dot. Sounds good? And then you already have here Q and Q complement. So what I did now, I made a feedback control for both set and reset. Do you guys agree? Let's see what is the consequence of doing this, how I'm gonna describe it. So I have to have a truth table, right? So the truth table, it has input and output. Do you guys agree? Inputs is SR and output Q complement. Somebody can tell me, can I put R before S and SR is the same? Okay. So how many states this table is covering?
4.
Right, 0, 1, 0, 1, 0, 0, 1, 1. M0, M1, M2, M3. So far so good? Now this is NAND. So also I need on a side to put the truth table for NAND, so it will help me to fill up this table, right? So I'm gonna put here X, Y, Z, 1, 2, 3, 4, 0, 1, 0, 1, 0, 1, 1. Then I know it's an AND, so it's AND and negated, right? So AND is basically it's a bunch of zeros and last one is 1. Flip it's gonna be 1, 1, 1, 0. Sounds good?
Are we just going over this as review?
Yeah, I'm doing this for NAND, and then I'll go NOR because that was the beginning of the sequential.
We did NAND first.
I did, but I will repeat it again in case that
Okay.
somebody's missing something. Anyway,
Gotcha.
you have to understand the elements of the sequential so you can move forward fast to the rest of the chapter and the rest of the chapters even, right?
Got it.
So now, how can we fill this table? We will see, right? We need to learn from whatever we have. So, if there is one input equals 0, so pretty much, the output, no matter what, it's gonna be 1. You guys agree? So if I put here S is equal 0, R is equal 0, correct? So I know that, one of the wire is 0. So basically my output here is 1. One also of the wire is 0. The output here is 1, right? Is there any fundamental logical thing saying that, 1 negated 1? No.
No.
Oh.
So that means undefined. Can't be used. Perfect. Okay. Now we're gonna go in M1. Okay, so we're gonna have a color here. And in M1, the color is 0, 1. So gonna be here 0 and 1, which is makes sense. If I set, I reset, right? I cannot set and reset at the same time. So, it's 0 and 1. So let's see what will happen here. So we're gonna clear up whatever mess we made here and we'll think about it, right? If it's 0, 1, how it's gonna work? So since this is 0, so the output is 1. Do you guys agree?
Yes.
Okay. Now, the second part of the table, if one of the input is 1, right? So then the relation between the second and the output is negation, right? Okay. What does it mean? Now this one is passed here, right? So 1 with 1, the output would be what?
0.
0, which is correct. So this state is valid, right? And the output coming out of it is basically 1, 0. Make sense?
Yep.
And it's understandable that, when I do this, it's going to be the vice versa, right? So it's going to be here 0.
1.
Now, what is the last thing? 1, 1. So in that case, I'm going to clear up my mess here. And I put here 1, and I put here 1. Make sense? Okay. So 1, 1, the table here said literally, if 1 here, so this branch will be an inversion of this, and this branch will be inversion of this, right? But I have no idea what is Q and Q complement is. So I'm gonna make assumption, right? Let's make assumption. What is my assumption? What about if Q equals 0 and the complement will be 1? What will be the next output? So let's see. I have here 1. I have here 0. That 0 will go here, right? So the 0 is 1. What the output will be?
1.
It will be 1. And that 1 will go here, right? 1 and 1, the output will be what? 0.
0.
So what happened? The previous input was 0, 1. The next output is what?
Stored.
0, 1. So it's basically what? Locked. So it's forever, this circuit will be producing 0 in the Q and 1 in the Q complement. If S and R equal 1, that means stored. That makes sense? Stored. Maybe somebody will say, but what about if I flip? What will happen? So let's see, right? So I'm gonna put this 1 and I'm gonna put this 0. So my previous 1 and 0. Let's see what will be the output, right? So clear up this here. And look at it, right? So here 0 is going up here. So 1 and 0, the output will be 1. And then that 1 will go here, 1 and 1, the output will be 0. So it's also gonna be the same thing, 1 and 0. So it doesn't matter what is the pattern in Q and Q complement, it's gonna be stay as it is. So we succeeded on building memory element.
Oh, the store memory is the memory element?
Yeah, I mean, I will ask you something, right? You build a circuit, right? And you would like to save something for a certain amount of time. What are you gonna do?
Just leave the pins where they are?
Exactly, but then there is a problem here. That's a very
Okay.
good, that's a good thing to show you the disadvantage of the latch. The latch store the data as I want, but it's stationary. What does it mean stationary? There is no a timer I have in my hand to say when it can flip. So I have physically, manually by my hand to change the S and R so I can let it go. Right?
Mhm.
Do you understand what I'm saying? So when I say manual, what is the idea of digital logic? Is to automate stuff, right? So if I put the human factor into it, so it's losing the purpose, right?
Mhm.
That makes sense?
Yeah.
Yeah.
Yeah. Now let's do the same study for the no latch, right?
Sorry, Professor, if you kept it in the store memory, would you use less power as well?
Not entirely true, because end of the day, there is something hooked by one, which is the voltage, right?
Mm-hmm.
So when you have one, that means you are sucking from the battery.
Okay, got it. Mm-hmm.
Right?
Yeah.
But of course, static movement is cheaper than dynamic movement.
Makes sense. Yeah.
Unless we will go into the clock, then we will see how it is very good. Okay? Now let's go to the SR NOR latch. So that means the elements will be used for building this latch are NOR. Do you agree? So here is my NOR gate. SR Q complement. Sounds good? Now we're gonna go into the color and go like this. We go into the color and go like that. Sounds good? We're gonna do the same thing, right? What is our tool? SRQ complement 1, 2, 3, 4. And then in our side job, XYZ, which is 1, 2, 3, 4, 0, 1, 0, 1, 0, 0, 1, 1. And they're gonna be NOR. So it's OR flipped. Do you guys agree? In OR, everything is one except 0, right? So that means it's gonna be 1 zeros. Sounds good? Now 0, 1, 0, 1, 0, 0, 1, 1. M0, M1, M2, M3. Okay, now we're gonna go into our table and see how we're gonna play this, right? So let's flip with 1, 1. I'm sitting. So basically here is 1, here is 1. And from the table I see here, if one of the inputs of the NOR gate are equal 1, period, the output will be 0. Do you guys agree? So pretty much I have no clue what is those, and I don't care. My output here will be what? 0, 0, which is translating that, this state is not useful, and it can actually cause the whole entire setup to crash. So that's undefined, not used. Sounds good?
Yep.
Now we're gonna go in the 0, 1, and 1, 0. So we're gonna clear up this.
Okay.
What's up?
No, I just said okay.
Okay. Anyway, so 0, 1. So S is 0, R is 1. So the one it has 1, I don't care what is the second input, the output will be 0. Do you agree? That 0 will go here. 0 is 0. That means it's going to be 1, which is going to be in that case. Q is 1. Q complement 0. You can flip it to be 0 and 1. Do you agree? Now we're going to play with the last part, which is basically 1 and 1. Sorry, 0 and 0. So when I have 0, the second input will be the official output negated, but I don't have it, so I'm gonna make assumption, right? So if my assumption here, this is 1 and this is 0, so that 1 will go here, so they're gonna be negated to be 0, and that will be 1. So what happened? The previous equal the next. So this is our storing state. So if I do a very close comparison, I will find out that, you know, S and R, same. What flipped out, 1, 1 will be storing, 1, 1 here is undefined, 0, 0 is undefined, here we're gonna be storing. Any question?
Can you do M2 again? For this one, the NOR gate, is it supposed to be flipped? Or am I doing it wrong?
Let me see. Anyway, so clear up here. What is the problem? Tell me. You want M2?
Oh, no, got it.
$5.
All yours.
You know, I keep counting, and I'm gonna guys send you my bank account.
Professor?
Yes.
What does it mean to be in a storing state?
That means, you know, did you see? That was 1 and 0, right?
Yes.
But, you know, after that, after 5 minutes, it's still 1 and 0. After 10 minutes, it's 1 and 0. After 1 million years, 1 and 0, unless I will change S and R. So what does it mean?
Storing.
Exactly. So I will give you a scenario. My latch, okay, it started to be 0 and 1. You agree? Then automatically, after the response of the two NOR gates, right, it came to be 0 and 1, so it's going to be 1 and 0. Do you agree? Then after 2 seconds, I decided to change my S to be 0 and 0. What will happen? From that moment to infinity, the output will be 1 and 0. So I locked it. When you lock something, you store it. When you are, for instance, in the lecture and you learn 1 + 1 is equal 2, you locked it in your brain. Since that day till now, you know 1 + 1 is equal 2. Make sense?
So you have to change the inputs?
Huh?
I said you'd have to change the inputs in order to unlock it, or is
Yes,
there?
of
okay.
course. That's one of the disadvantage of the latches. It's advantage, yes. From combinational, we build something to store data, but it's not controllable. It's not fully controlled by time. Make sense?
Professor?
Yes.
I'm sorry, but I don't really see it. So you're saying that after having S and R to be 0, we're gonna have the output to be 1, 0, but after when we change the output, the input, and maybe we go from, okay, now I'm confusing myself.
I think so, yes. Think about it, wait. I put here the, you know, I just came and I found you left me on my disk as our latch circuit. Then I played on it. Then what I did, you know, cool. I put in S0 and I put in R0, 1, right? Then I found in front of me, Q is LED is turning on and a Q complement LED is equal 0, which is turning off, right?
Yes.
Then I said, you know, Muhammad, you know, I'm gonna make S and R now 1 and 1. Sorry, 0 and 0, because 1 and 1 will be undefined, right? What will happen?
Stays on the
It'll
last
keep-
state.
It's
It'll
still
still
gonna
have
be
it.
like this forever until your battery will be off. So what
So-
I did, I stored whatever you give it to me.
So by using the NOR gate, because you set 0, 0 as storing, would you use less than NAND gate?
Now we are
Energy-wise?
now we are talking about a very interesting aspect, which is how much power you can consume or not. I like this. That's actually show you how you are thinking even beyond the circuit. So what's your name again?
Yoichi.
Yoichi. Okay. So
I'm gonna join your team.
yes, you are in my team now. All the money I took from you guys, I will give it back to you. Okay. I took it virtually, Okay. No, seriously. So it's really good, NAND technology used for some application, no technology used for some other application. Do you agree?
Yes.
Yeah.
NAND, people say sometimes storing is actually less power. Some other time they say no is less power. So it depends on the concept and where exactly you're putting it. For instance, SSD, right? Do you remember the SSD flash drive and stuff like that?
Mm-hmm.
You will find it's written NAND technology.
Really?
Yeah.
Okay.
The little IoT devices, NOR technology. I watch the whole entire semiconductor NOR technology.
So cool.
Does it have anything to do with size? No, right?
It's not size, power. And size also. Because, if you look to the VLSI concept, we have something is called CMOS, which is complementary metal oxide silicon. Complementary metal oxide silicon. That's what's actually CMOS transistor. How it is basically one transistor holding holes and the other holding electrons, and I'm connecting them like that. So this setup, this is input and this is output. This is actually inverter. This is not gate.
Oh. Okay.
Okay. You know what is holes and electrons, right? I will tell you a story. Okay. Here, Muhammad. And here, Gabriel. Right? And then, we build you a channel between us, right? And he's throwing the ball to me and I'm getting back the ball and so on. So what we are doing now, we already open a channel and we're playing volleyball, right? That's the same thing as the electrons in your wire. So it's a bunch of electrons going in a queue from the source to the destination back and forth. But since, in the physics, they say there is movement of carrier, can be electrons or it can be positive charge, which they call it holes. So the transistor who is based on the electrons, they call it what? NMOS. NMOS. The one based on holes, they call it PMOS. This is the P and this is the N. And then you put them together like that, push the data. Then I don't know if how much of information you know about transistor, but I will tell you that transistor. Imagine that we are in a war zone. I don't know, maybe, and then there is the check gate. Don't say it in a war, would be more nice. We are going to visit the Science Museum in California here, right? So everybody in a row like this, in a queue, and then there is a security guard checking your ID and you're getting in, right?
Yeah.
This security guard is the gate. So the transistor like this. VCC, ground, gate. So if I push like this and open the gate, the current will be running, right? So Muhammad will be visiting the Science Museum. If the security doesn't like me, it will open. Muhammad will be staying here. This is the transistor.
Okay.
Make sense?
Kind of.
Don't worry. After the pandemic will be over, just come to my office. I will describe it to you with even, with bunch of the.
Would you let us in, or are you gonna be the gate and not let us in?
You know
Oh,
what? I will hire a bunch of transistors outside, you know, to check on you. Yes. Okay, sounds good.
Mhm.
So imagine the chip you have in any device, any chip, you know, whatever chip you have ever seen on a motherboard or whatever, right? Is a billions of these transistors.
Billions.
Billions. Of course, historically, it was like, you know, have you heard about vacuum tube?
Yeah. Mhm.
Yeah, vacuum tube. Then, you know, they said, oh my Lord, our computer is like 3 stories. Then, you know,
Yeah,
they
yeah,
started to, you know, make it like 4 or 5 transistors on that chip. They call it IC, integrated circuit. Then they start to have it moved in. They call it what? VLSI, very large scale integrated circuit. Then they make it what? UCLI, which is the ultra scale, whatever. Then they will move to the other one up to they start squeezing the size of transistor and then say more transistor on the chip.
Yeah.
Okie dokie.
Mhm.
Now, in the in the last lecture, I told you about something is called clock.
Yes.
So we figure out, you know, one of the disadvantage we have for this latch is basically what? The limitation for using all available states we have, which is if you are NOR, it's gonna be 1-1. If you are NAND, it's gonna be 0-0. But as a designer, I should use all the states. Do you agree?
Yep.
So that's one of the disadvantages of the latch. The second advantage, it is static, it's stationary. That means, you know, I have to come physically by my hand and I put setup on SNR so I can keep Q and Q complement fixed. So there is no timing aspect at it. So we have to find a way to add the timing aspect by defining something in the circuit course I'm sure you guys are taking, which is called RC circuit. Charging, discharging using passive elements. But I have a news for you. There is no resistors and capacitors inside your chip. What you have a transistor acting as a resistor and other transistor acting as a what? Capacitor.
Capacitor.
Exactly. Why? Because if you look to the transistor in general, it's like this. That's called substrate. And then, you know, you already have here little. And this is the gate, this is the source, this is called the drain, and this is what? Metal oxide silicon. So basically, you know, if you look to that capacitor is like 2 plates, one is positive or negative, and here dielectric, right? So that's acting like the dielectric. So in some characteristic of the transistor, that will be acting as a capacitor. Some
So it
others
behaves the same
will
way?
be acting as a resistor, yes.
Okay.
Anyway, back to the future. So, you know, we need to have an element will be very fantastic use for timing the future circuit will be working with time. So they build the crystal. You remember the crystal?
Yes.
The crystal internally, it has switches, as one of you told me last time, because, you know, if I just like literally harden the capacitors with resistors, it will discharge forever, right? But, you know, we need to charge, discharge, charge, discharge, discharge, discharge. So basically the switches will be like the boom, 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 right? And the consequence of this would be charging, discharging, charging, discharging, charging, discharging forever. But, you know, this is a kind of distorted signal to be mature enough to be used. So, you know, do you think about, you know, tau as a time constant, time R times C, the change in the values of the R and C, so it will turn to be like what? Smoothing this sharpness to the ground is here. Then, you know, again like this, like that, like this, like that, forever. Make sense? Now we're gonna go into the conclusion that, you know, we have this like this and this like that. Then we came into the conclusion, any signal look like this, they call it what? terrain of pulses, but it has to be also ready to be used. So it has to have some of the criteria, and the criteria to make this signal ready for us as a digital logic designer, it should have fulfilled some requirement. One of the requirements, this period of time, it should be equal this one forever, and that's called what is called T uppercase or capital letter, and it's standing for the time period. So it's replica, and based on this replica, when I keep repeating, I define something is called what? Frequency. How frequent this is happening, which is basically 1/T. So you get the T, 1/T. So unit wise, T, it's made from the nanosecond, millisecond, picosecond, and second, and even microsecond. Okay, so it's second time, right? Millisecond, the pin 10 power minus 3 s, 10 power minus 6 s for the micro, for the nano 10 power minus 9 s, for the pico is 10 power minus 12 s.
Oh.
There is even fs, which is the femtosecond, 10 power minus 15 s. You guys know the story of the femtosecond?
No.
Let me tell you a nice story. We are having spring break soon, so I can give you general information. So normally people, when they start looking to the time, they don't make a new unit of time unless they observe something happening in that new time window they actually have. For instance, why millisecond is millisecond? Because they found out many phenomena on the ground, on the earth, on the universe, happening within this time slot, and they call it millisecond. Microsecond is the same. They came into picosecond and they stopped. Anything else is theoretical. Muhammad told you guys 10 power minus 18 second. Oh, cool. Muhammad is saying anything. Okay. But then they came into, there is a professor from Caltech, California Institute of Technology. He's Egyptian, actually. He passed away. He got a Nobel Prize. His name is Zowail. And his team built a camera made from the laser beam to record the reaction between sodium molecules for merging together for building a certain chemical reaction within 10 power minus 15. And he named this femto. So it's called femtosecond.
Oh. Interesting.
So imagine, for instance, Gabriel and Andrew came with Muhammad, and they built together a new reaction between something and something. And while they are counting, they found it 10 power minus 18. Then, we will make our own unit. And, we will take the Nobel Prize. Of course, I will take the money, and then I will send you thank you letter. Sounds good?
Yeah.
Yep.
Fair enough.
Mm-hmm.
Now it makes sense?
Yes.
Okay. Now, what about frequency? So the guy, he actually was looking into the frequency. His name is Hertz. So, they actually united for him to be HZ, standing for Hertz. He's German.
What's his full name?
Hertz. So in Hertz, you have HZ. It can be Hertz, K Hertz, M Hertz, G Hertz, T Hertz. You know what's this? Kilohertz. That means 10 power 3 of Hertz. M mega 10 power 6. G is gigahertz, 10 power 9 hertz. T terahertz, 10 power 12 Z. If you notice something, the flip of those.
Do they all have stories as well?
Yeah, so basically hertz is what? is 1 over s second. Right?
Mhm.
Anyway, cool, we learn time periodically happening, we learn frequency, but also we need to remember what the configuration of the internal signal, which we call the on-time duty cycle. What is the unique in the clock? It's actually the on time equal off time. So T on equal T off. So pretty much T is equal T on plus T off. You can call it T is equal 2 times T off, T equal 2 times T on, whatever you want. Cool.
Yep.
If this happen, then whatever signal I see on oscilloscope is considered what? Clock. Then if it's a clock, we have to look into how I'm gonna use it, right? So if I want to look to how I'm gonna use it, I'm gonna look to something that's called levels. I'm gonna look for something that's called edges. Level, here is my level. This is level on, level off, level high, level low. So 2 levels. So I can write it down here. Levels will be what? On or high, level, off, or low level. Right? Edges. Edges is basically what I'm gonna use with you for the flip-flops and anything sequential, which is the event while I'm changing my state from low to high or high to low. So that's basically it's called edges. How can I define it? Let me get a very fancy color. So I'm going from the low to high. So this is the sharp line is the positive edge. They call it pos edge or rising edge. Pos or rising. So we're gonna put it here. So you have pos or rising edge.
Mhm.
While there, I'm going to charge. So basically, I'm from the, I'm sorry, I'm discharging. I'm sorry. So from the low, from the high to the low, I'm losing a charge, right? So in that particular moment here, that will be my negative or falling edge. Flip-flops as a sequential essential elements are working and reporting outputs or movements between input and output in the characteristic based on the edges. Cool.
Yep.
Yep.
Any question? Any answer? Any concern? So flip-flop works on edges of clock. I can stop here if you guys want, and we can continue next time because I don't want to keep adding. So, you know, I will destroy your spring break. Which way you prefer? Which way you prefer?
I'm genuinely curious to see how you implement a clock.
I love this. You know, see this guy's like, you know, you're gonna work with me, okay?
Okay.
Okay. So we build a latch. Do you agree?
Mhm.
But we hate a latch. I don't like latches. So literally, actually, when you will go into the digital logic design, advanced digital logic design with hardware description languages, you will find your professor telling you what, don't ever use latch, don't ever use latch, don't ever use latch. And you keep saying, you know, why does people say what, don't ever use latch? Then you will remember Professor Ali told you what, latch is uncontrollable. You cannot control it. It's cool, but you cannot control it. And we have to be aware to control everything in our hand, so everything it will be scheduled. So designers and mathematicians came into a conclusion, SR latch is not bad, but we need to add some aspect to have time on it. And they build the first flip-flop, is called SR flip-flop. Perfect?
Yeah.
How does this SR flip-flop look like? It's not really hard. Basically, the latch and external component for the latch. What does it mean? So you're gonna have here, if this NAND, for instance, right? I'm gonna put here extra NAND. Somebody would tell me, hey, why are you putting this extra NAND? I will show you. Because you can put here R, you can put here S, and there you can use the clock. Make sense?
Kind.
So what does that? What does this do?
Very good. This actually is controlling RNS. Right? I will tell you. I have the computer, the laptop of Leslie. I have the laptop of Gabriel. And I would like to control both of you. Then I will bring a switch and I will bring the power supply of both of you and connect it to the switch. Then I will have external the power cable in my hand. Then I will be teasing you from the end of the corridor, telling you, should I connect it to the outlet or not? Should I connect it or not? That's the same thing. I'm having the power in my hand now, right? I'm telling SNR, be nice so I can pass your signal. That makes sense?
Can you repeat that one more time?
Again, now, this is the power supply of Gabriel. This is the power supply of Kushal, right? Both of you, right? Now, those need to be connected to the what? To electricity. So you get the, you fill the battery with juice, right? Yeah. So in that case, if I come and tell you, I would like to control those guys, what should I do? You know what? I will tell you there is just one outlet, and then I will bring a switch, the power outlet thing, right? I will take your cable and I connect it in that switch. And I put your, Gabriel cable and I put it in the switch. Now, if you guys, both of you would like to be working, what should I do?
Turn it on.
Turn on what? I have to take the extra out and connect it into the power in the wall, right?
Yeah.
That power in the wall is a clock. Enable.
Oh, it's an arbitrary thing where okay. Okay. So I thought you were making a physical clock with like counters. Okay.
No.
Oh.
Building the circuit for the clock, it's analog.
Oh.
We are digital. Okay. We just need to know the characteristic.
Oh, okay.
There is something in the, I used to work for Atman. How many of you heard about Atman? You guys don't know Atman. You don't know Arduino.
Oh, at Mega?
At Mega. My team built at Mega.
Oh.
So I was working in the design house in Norway. And the at Mega was built in Norway. Then the Italian guy from Arduino, built Arduino and he started using our stuff and it went everywhere. He called it Arduino. He's Italian.
That's pretty cool.
So do you determine what kind of edge S goes on and what kind of edge R goes on?
No, okay. It's not determined. Basically, this thing, did you see the whole entire building now in front of you? Will be symbolized like this. S, R, Q complement. And look at this, look. what is this meaning? It means this device has to be working on the edge. And in this kind of configuration, since I made it like this, right? So that's called, this device is reporting in the positive edge. Somebody will tell me, what about negative edge? Then I can tell you, you can do it like this. They're gonna be negative edge device.
So it's either or, not both?
You cannot be both.
Okay.
I have a use patent made both. That was granted last year in May 26. Then, you know, that was about memory. Then Intel built something in the top of mine, and they make their own for AI. And of course, they refer to me. That's fine. I will see how I'm gonna get my money from them. You know? It's not fun. The patent was sponsored by the US Department of Defense. Okay, doke. Any question? Any answer? Before I move forward, should I move forward or should I stop?
So the clock is coming from the crystal.
The clock is coming from the analog.
Analog,
right?
completely analog, because RC analog, right?
Mm-hmm.
Then, you know, you're gonna work on something that's called analog to digital co-simulation. Because, you know, think about it, right? My microphone is analog, but, you know, my computer is digital, right? How I'm gonna make both of them talk to each other? Make sense?
So does the signal that's coming out of the crystal, is it already a square,
Exactly.
square wave?
Yes, sir.
Oh.
Yes, sir. We shape it like that, see? It used to be ugly like this, but then you have a tuner that will tune this shape to look like this. And based on the size of the RNC when you time them together.
So
and we make analog filters and stuff like that.
So before we had the crystal, we used to use RC circuits.
Inside the crystal RC circuit.
Oh, inside this crystal's RC circuit.
So yeah, the crystal. Do you remember? It's like a silver thing, right? Yeah. If you open it, there is in the design there is bunch of resistors, and capacitors, and you know reliable and relays and many things. But who is fundamentally generating this, you know, periodic thing? Is the crystal and the RC inside the crystal. Oh. The brain of the crystal.
Oh, so it's not like a real crystal. They call it a crystal?
They call it crystal.
Oh, okay, got it.
Because there is something that's called in the in physics, pseudo. I think pseudo, right? It's a type of material. If you squeeze it, it will bring electricity. If you apply pressure on it, it brings electricity.
It changes from it changes from one type of energy to another type of energy?
Yeah, it's kind of that, yes.
What?
Yes, yes, yes. Have you heard about quantum?
Yes.
I heard the word quantum, but I don't know what.
Yeah, I have my team. I have my team now working with quantum computing.
Jeez. Whew.
It's more fun than this, you know. One day when the quantum machine exists, all of these gates would be in the trash.
Yeah, but right now I can only do basic math, right? Quantum.
Yeah, quantum, you know.
I can't do like what we need right now.
The quantum now, the quantum exists, and is the one is making quantum exist is crypto security, because the quantum succeed on theoretically. The quantum machine can run algorithms called Schur algorithm, which is used for the prime factorization. And 99% of the used crypto primitives are based on the prime numbers. So if you make factorization with quantum machine, I can break your bank account in 1 hour, less than 1 hour, instead of using the 15 supercomputer to figure out your key. Okay, it's another story. I don't want to put too much in your head. Yes. Okay, 10 minutes, it's not as significant. So I would say that, go relax, watch TV or whatever before you would go to the next lecture. But at least we build the basis. And next time we'll be start pushing onto the 3 tables for the S, R, J, K, and why JK exists, because actually it's trying to solve SR problems. And while they are solving the problem, they came with a new problem. They turned this problem to be something used, and they call it T flip-flop and D flip-flop, and will be covered by all of the elements used for sequential circuit. It is nice to know history of the story, and you combine it with the physical meaning with the mathematical meaning, then you will be covering the whole entire story.
Yeah, I feel like we should have a history class.
Yeah. You can come to me. That's fine. I can give you history. $25 per hour. Okay. Any questions?
Just making sure. So the clock controls the latch, correct?
It's not latch anymore.
Well, it's not latch, but it's flip-flop now.
It's a flip-flop.
Yeah, see? This is flip-flop.
Yeah.
Idoki ok.
Yep.
Since it's a flip-flop, so we have to study the present and the future, and which is basically the call is recursive return, right? So I will show you something. If you build a combinational circuit like this, here is your input, and that output came into like that, right? And then you get like this, right?
Mm-hmm.
Now, the input output will determine what will happen to that the flip-flops later on. So that's why, one of the table are the inputs and the Q. Second will be the Q with the input and what will be the next state. And then the third will be the present state and the next state, and will determine what is the input. So that will be the truth table, that will be the characteristic or the state table, and that will be excitation table.
Okay.
Okay?
Yeah.
Done for today. It was my pleasure to talk to you. And I have fun with you guys. That's very cool. And I hope that also you have fun. I apologize for being slow for delivering your grades for the first midterm. I promise in the spring break, I will do my best to grade everything.
Oh, it's okay. Take your time, sir. It's fine.
And there is a room for improving. Don't worry. It's not a crisis. We still have the second midterm and we have the finals. And who knows, maybe, I can invent something in the middle. So don't worry. So
like an extra credit or something like that.
Something, who knows, God knows, I don't know it so far. But anyway, I want you guys to just enjoy the science more than just like, fear of grade.
Definitely. Thank you, sir.
Okay. So if there is no questions, I would say, God bless all of you. Please stay healthy and wise during the spring break. Don't go for parties and stuff like that. And I will see you after the spring break. God bless all of you and have a nice weekend as well.
You too.
Thank you. Thank you. God bless. Bye.
Thank you.
Thank you, Professor.
Bye-bye.
Thank you, Professor.
Thank you. God bless. Bye-bye.